In this lesson, we will continue to study examples of a group before we formalize the notion of a group in a future lesson. So let's start with an example. We'll let sigma be a function whose inputs are the numbers 1, 2, 3, and whose possible outputs are also 1, 2, and 3. And this notation is a function notation, and we'll talk more rigorously about function notations later in the course. But for now, just know that the name of the function is sigma, inputs are 1, 2, 3, and the possible outputs are also 1, 2, 3. And so here's the definition. Sigma of 1 is 3, sigma of 2 is 1, and sigma of 3 is 2. So we say that sigma is a permutation of the set 1, 2, 3 because it shuffles the three input numbers 1, 2, and 3. And we get the outputs 3, 1, 2. And notice that all the outputs are different. That's the effect of shuffling the three numbers 1, 2, and 3. Here is something that's not a permutation. So here is a non-example. So consider this function f, whose inputs are also 1, 2, and 3. But notice how the outputs, f of 1 is 2, f of 2 is 1, and f of 3 is also 1. And notice how we have these two outputs that are the same. And so f is not a permutation of the set 1, 2, 3. In order to be a permutation, all the outputs have to be different from each other. Let's continue looking at an example. We'll have two permutations now, sigma and tau. And here are the definitions of those two permutations. So sigma sends 1 to 3, sigma of 2 is 1, sigma of 3 is 2. Notice the three outputs, 3, 1, and 2 are all different. So sigma is in fact a permutation. And tau sends 1 to 2, 2 to 1, and 3 to 3. And so tau is also a permutation. The three outputs are different. Now, we'd like to find a way to combine those two permutations, sigma and tau, and come up with another permutation. And so since sigma and tau are both functions, we will compose them to obtain sigma composed with tau, which we claim is another permutation of the set 1, 2, 3. And so let's do a function composition calculation. So we have this composite function sigma composed with tau, and let's see how that acts on the input 1. So sigma composed with tau of 1 is the same as sigma of tau of 1. And notice tau is the inside function here. Now tau of 1, according to the definition, is 2. And then sigma, notice, is the outside function, so that gets applied after tau. And sigma of 2, according to the definition, is 1. And so ultimately the composition sigma composed with tau sends 1, 2, 1. Now let's go to the input 2. So sigma composed with tau of 2 is the same as sigma of tau of 2. And tau of 2 is 1. And then sigma of 1, sigma is the outside function, sigma of 1 is 3. And so as a composition, sigma composed with tau sends 2 to 3. Now, if we're believing that sigma composed with tau is also a permutation, then its three outputs have to be different. So if the first two outputs are 1 and 3, let's hope that the final output is 2. But let's actually verify that. So sigma composed with tau of 3 is sigma of tau of 3. Tau is the inside function that gets applied first. Tau of 3 is 3. And then sigma of 3 is indeed 2. And so that fortunately checks out. And so sigma composed with tau is also a permutation of 1, 2, 3 because its three outputs are different. And I'd like to just mention that this is just like composing symmetries of a square that we studied in the last lesson. Now, instead of the inputs being a square, they're just numbers 1, 2, and 3. Now, just as we collected the symmetries of a square into a set called D4, we're going to collect all the permutations of 1, 2, 3, like sigma and tau that we just saw in the previous slide, and we'll call that set S3. The S stands for the word symmetric. S3 is often called the symmetric group. So let's do some calculations this time. We'll ask you to do it. If you could pause the video. There are three permutations here: sigma, gamma, and epsilon defined as follows. And if you could compute epsilon composed with sigma, and then also sigma composed with gamma, and see what you can find if you notice anything interesting. So please pause the video and do those two computations. All right, well, let's take a look at sigma composed with gamma. So I claim that sigma composed with gamma is actually epsilon because of the following. So I'll do this calculation. It's the second time around, so I'll do it a little more quickly. Sigma composed with gamma of 1 is sigma of gamma of 1. Gamma of 1 is 2. And then sigma of 2 is back to 1. So ultimately, the composition, sigma composed with gamma, sends 1, 2, 1. How about the input 2? Sigma of gamma of 2. Gamma of 2 is 3, and then sigma of 3 is back to 2. All right, so composition sends 2 to itself. And then input 3, so sigma of gamma of 3, gamma sends 3 to 1, but then sigma sends 1 back to 3. And so we have this relationship that sigma composed with gamma is epsilon. Epsilon, by the way, is a somewhat boring permutation. It basically does nothing. Perhaps the name epsilon is appropriate there. It sends 1 to 1, 2 to 2, and 3 to 3. And so the composite sigma composed with gamma also sends 1 to 1, 2 to 2, and 3 to 3. So its behavior is the same as that of epsilon, and that's why we have this relationship. Sigma composed with gamma is epsilon. Now what about epsilon composed with sigma? I'll leave the details up to you, but you should have found that epsilon composed with sigma is just sigma. So epsilon's really the do-nothing permutation. And I'll certainly say a little more about these calculations, make some generalizations about these in the next slide. Here's the permutation epsilon that we just worked with. It's defined in the following way. It sends 1 to 1, 2 to 2, and 3 to 3. So in a way, it's a bit of a boring permutation. It does nothing to its inputs, but it's perhaps the most important permutation. It has the following property that epsilon composed with alpha is alpha. It keeps alpha unchanged. And the other way too, alpha composed with epsilon is also alpha. It keeps alpha unchanged for all alpha in S3. This is very much analogous to if you're using numbers, multiplying by 1, or if you're adding 0. And perhaps not surprisingly, we'll call epsilon the identity permutation in S3. Now, we also saw in the previous calculation that sigma composed with gamma was equal to epsilon. And I'll leave it up to you to also verify that gamma composed with sigma is epsilon as well. And so we say that sigma and gamma are inverses of each other. And we write that gamma is equal to the inverse of sigma. And we can also say sigma is equal to the inverse of gamma. This relationship is very much like saying 3 times 5 is equal to 1 and use 7. 3 and 5 cancel each other out under multiplication, and we can think of sigma and gamma canceling each other out under composition because their composite, or product, is the identity element epsilon. We'll introduce a notation to represent a permutation. So here's sigma in S3 once again. The inputs, as usual, 1, 2, and 3, and the corresponding outputs are 3, 1, and 2. And so here is sigma written in what's called a matrix form. And sigma equals, and here's the description of sigma. The top row for S3 is always 1, 2, and 3. If we are looking at, say, S4, permutations of the set S4, then the top row would be 1, 2, 3, and 4. But this is an S3, so top row is 1, 2, 3. And the bottom row are just the corresponding outputs. So in the case of sigma, it sends 1 to 3, 2 to 1, and 3 to 2. So the bottom row would be 3, 1, 2. And this says that it sends 1 to 3, 2 to 1, and 3 to 2. So this representation, the matrix form, has a benefit of really treating sigma as an object. I mean, it is a function, yes, but it allows us to view sigma as a function. It also allows us to talk about a permutation without a name like sigma. We can just focus on this part without the sigma and say, here's a permutation. And we don't necessarily need a name like sigma attached to it. And sometimes we'll do that as well. At this point, please pause the video and work on day 6 classwork. And afterwards, we'll go over some of the problems and concepts. In problem 2, we proved the following statement. Let alpha, beta, and chi be an element of S sub n if alpha composed with chi equals beta, then chi equals alpha inverse composed with beta. So before we write down a careful proof of this, let's do a little bit of scrap work. And in the scrap work, I'm not actually going to talk about this particular implication, but something related and perhaps a little more familiar. And namely, it's the task of solving the following equation. 5 times x equals 17. Now, this is not a trick question. X is 17/5, as you might imagine. But thinking carefully about why x equals 17/5 in this equation and how to solve for that will give us a lot of insight into proving this particular implication. And I might mention that alpha chi equals beta is very similar to 5x equals 17. And notice how we're, in a way, solving for chi here, just as we're going to solve for x here. So how do we solve for x? Well, we would divide both sides by 5, or let's use multiplication. Multiply both sides by 1/5. And so if we do that, let's see what we get. So we'll multiply both sides by 1/5, and we get the following. 1/5 times 5 times x is equal to 1/5 times 17. So here was the original equation, 5x equal to 17, and notice how we multiply both sides on the left by 1/5. Now, ultimately, we want to see that this equals x, and we can see that 1/5 and 5, they cancel each other out, we get an x, but let's go through that argument a little more carefully. So working on this left-hand side, what happens? Well, by regrouping, or by using the associative law and moving the parentheses around, this becomes 1/5 times x, 1/5 times 5, and then times x. But now 1/5 times 5 is the same as 1 times x, because these are multiplicative inverses of each other. And then 1 times x, 1 is the multiplicative identity, 1 times x is just x. And so this whole left-hand side simplifies to just x, and therefore we can conclude that x is equal to the right-hand side, namely 1/5 times 17, or if you like, 17/5. And so let's apply that thinking to our proof about permutations. As usual, I'll begin by identifying the hypothesis and the conclusion. So that gives us already the very first line of the proof, assume alpha composed with chi is equal to beta, and the very last line of the proof, thus the conclusion, namely chi equals alpha inverse composed with beta. So how do we proceed? Well, we start with this equation, and just as in the scrap, we multiply both sides by 1/5, which, by the way, is the inverse of 5, multiplicative inverse of 5. Let us compose on the left by alpha inverse. And so here is the original equation, alpha chi equals beta, and we just compose both sides on the left by alpha inverse. Now, as we did in the scrap work, we are going to work on this left-hand side. And we already see that the alpha inverse and alpha cancel each other out. We're going to be left with just chi, but let's go through that argument a little more carefully. So the left side of this equation becomes the following. So we start with this. That's the same as the left side here. We move the parentheses around using the associative law, regrouping, and so we have alpha inverse and alpha together now inside the parentheses. Why do we do that? Well, because alpha inverse being the inverse of alpha, we see that alpha inverse composed with alpha is the identity permutation epsilon. And what's next? Well, epsilon times anything is that anything. And so in particular, epsilon composed with chi is just chi, because epsilon is the identity element. And so what we just showed is this entire left side simplifies to just chi. And so by replacing this left side with chi, we get chi is equal to alpha inverse composed with beta, which is what we wanted to show. And so once again, this is these two calculations, solving 5x equal to 17, or in a way solving alpha composed with chi equals beta. We use the same principles like the inverse element and the identity element. These are both important group properties that we'll formalize in a future lesson. But for now, that's the end of this proof and also the end of this lesson. So I will see you next time.